This is a lecture for AP Physics 1, Unit 6, Part 3, Angular Momentum. We've been talking about the motion of rotating objects or systems and comparing them to things that we learned about linear systems earlier in the year. So one of those properties that all moving objects have is called momentum. Momentum can be thought of as inertia in motion. It's the tendency of an object to keep moving in a straight line at a constant speed. So an object that is rotating has momentum. For example, if you push a disc or a ball, anything round on a flat surface, it's going to attempt to move uniformly in a straight line. Now, at the same time, if it was a ball or a disc, it would also be rolling. And so that rolling disc has another tendency. Specifically, it will attempt to continue to rotate at a uniform rate. It'll attempt to keep going in a straight line at a constant angular velocity. We call this tendency angular momentum. Formally defined, angular momentum, usually designated with a capital L, is the measure of the tendency of an object or system to continue in uniform rotational motion. It is directly dependent on the moment of inertia, usually designated with a capital I, and the angular velocity, designated with the Greek letter omega, and it can be for an object or a system of objects. So the formula for angular momentum is L equals I omega. Now keep in mind that a rotating object can have both linear and angular momentum, such as a person on a bicycle. The wheels may be rotating, and so they've got angular momentum, but also moving forward, and so they've got linear momentum. Now, you could have a system in which the axis is constrained to be in one place, like this bicycle turned upside down. Now, if you roll the wheel, it will only have angular momentum. But you should keep this in mind that it could be two things. If you had a bicycle that you tried to stand up, you'd have to prop it up in some way if it is not moving. You know why they fall over? Because they're too tired to stand up. Ha ha. Anyway, here you can't see it very well, but there's a kickstand on the back of this bicycle that's holding it up. But if it's in motion, it can stay up all by itself. So with linear momentum, that was a vector quantity. Angular momentum is also a vector quantity. It has a specific direction. I don't believe that the AP curriculum requires you to learn the right hand rule, but it's really very simple. If the object is spinning in a certain direction, you curl your fingers in that direction, and whichever way your right hand, you curl your fingers of your right hand, and whichever way your thumb is pointing, that's the way the angular momentum is directed. But anyway, we're going to follow convention and say that if it's spinning and counterclockwise motion, we're going to call that positive, and if it's clockwise, we're going to call that negative. But anyway, the most important thing is that in real life, what all this means is that if you have an object that's spinning, it's got this angular momentum, the tendency to keep going in a straight line at a constant speed. And if you change its direction, if you change its angular speed, then you're changing its angular momentum. But objects are going to resist those changes. Now, in AP Physics, we're going to run into two situations. One is where we have what's called a point object. So in this case, it's not really a point, it's a basketball in the picture. But the situation we have here is maybe there's a hand holding it, there's a string that the basketball is attached to, and they're swinging it in a circle. So a point object revolving about a fixed point, you could find the angular momentum as a product of the distance between where it's pivoting to the center of mass of this object times its linear momentum. Now, linear momentum is a product of mass times velocity. So you could have this formula here that the angular momentum equals the radius or the length from the pivot to the center of mass times the mass of the object times its linear velocity. That's one way to find the angular momentum if we're doing something like this with a point object that's rotating about a fixed axis. This could be also like, say, the sun and the earth. Okay, it doesn't have to be an actual string, but it has to be some kind of application of a force here. The other situation is when we're looking at an object itself and it's spinning on some sort of internal axis. We're going to call that an extended object. So in this case, our formula looks a little different. It is the product of mass times acceleration, or the angular equivalence of those. So the angular equivalent of mass is the moment of inertia, I, and the angular equivalent of velocity is the angular velocity, which is designated with omega. So L equals I omega. That's another way of finding angular momentum. And usually that's applied to an object, like I said, that's spinning about its own axis somewhere internally. If you do the units of either one of those formulas, you should get a mass, two distance units, meters times meters, and a time unit. So here's a little example problem. Let's assume that we've got, say, a hand here, a basketball here, and we're swinging it around. It's 0.28 meters from our hand. The ball weighs 1.1 kilograms, and it has a linear velocity of 3.2 meters per second. So what is its angular momentum? Well, it's just the product of the variables that are shown on the screen. And so if we multiply those all together, we're going to get just about 1 kilogram meters squared per second. Here we have an extended object. It's rotating about an axis. This is a rigid disk of some sort. It's rotating at an angular speed of 12 radians per second in a counterclockwise direction, so that's positive. The moment of inertia is given as 15 kilogram meters squared. What's the angular momentum? Again, it's just the product of the two variables that we have. All right, I times omega. So it's 15 times 12 is 180. Our units. The radians go away. They're not really units. It's just a designation, but they can kind of come and go as they please. Also note that you can have an object that's got more than one angular momentum. So this bicycle's got two wheels, and so here's got angular momentum, and here's got angular momentum. The total angular momentum of this composite system is equal to the sum of the angular momentum of each of its component elements. So the total momentum is angular momentum 1 plus angular momentum 2 ad infinitum. Another way to look at that is we could have a formula for each one of these. So for example, we could use mr squared for our I and then omega. And so your formula would turn out looking something like this. It can get pretty complicated pretty fast. In AP Physics, it's typically limited probably to 2. And questions they like to ask are, like, if you've got a wheel that's spinning or a disc that's spinning, what happens if you add now something else to that? So you've got a second object that's also spinning, and it's, so it's got its own linear and angular momentums. So linear momentum can change if you apply a force over time. We call that an impulse. In the case of angular momentum, what you do is you apply torque over time. So a change in linear momentum, or an impulse, is equal to torque times the amount of time that it's applied. Now, torque is a vector, and so we got to pay attention to this, which direction it is, as opposed to which way the object was originally moving. So here's an example problem. A person exerts a 2.5 Newton force perpendicular to a lazy Susan which has a diameter of a radius, excuse me, of 0.26 meters. And this torque is applied for 0.15 seconds. Determine the final angular momentum of the Lazy Susan if it starts from rest. So its initial angular momentum is 0. Assume friction is negligible. And then second problem, find the angular velocity of the Lazy Susan, given that its mass is 4 kilograms. And you can assume that its moment of inertia is the same as a uniform disk. In other words, the formula for moment of inertia of a uniform disk is 1/2 mr squared. So gather up everything that you know: force, radius, time, mass, the initial linear momentum, and the change in linear momentum is going to be final minus initial, but initial is 0. So the change in linear momentum is just going to be the final linear momentum, which is what we're asked to find in part A. I left A out of the problem up there, but this determine the final angular momentum. So here is our angular momentum equation in general. It's the torque times the change in time. We don't know torque, but torque is equal to the lever arm times the application of a perpendicular force. And it says that the force was applied perpendicularly at 2.5 newtons. And the radius is 0.26. So let's multiply those two together and multiply time. And that will give us a final linear momentum of 0.0975 kilogram meter squared per second. So that's the answer to part A. Part B, we can add what we just learned in part A as a known now. And what we're being asked to find is the angular velocity at the end. I'm going to designate that just with an omega instead of with an omega sub f. So our other formula for an extended object's linear moment or angular momentum is its moment of inertia times its angular velocity. What we're trying to find here is the angular velocity, and so I'm going to rearrange this formula. I know this value. I just found it. I know this value because, I don't know that value. I've got to find I, so let's do that first. So it's 1/2 mr squared. It gave us the formula at least. We do know the mass, 4 kilograms. We know the radius. We're going to square that, multiply by 1/2. Don't forget to do this squared part right here. So here's our moment of inertia, 0.1352. Substitute that in here. We'll take this value and substitute it in here and do the math, and we're going to get 0.721. Originally, if you did all the units, this K and this M squared is going to cancel, and you're going to be left with per second. But we can always throw in the radians because that's what we're talking about here. So an angular velocity, how fast is the angle changing? It's changing at a rate of 0.721 radians every second. And so that about does it. That's the end of this little lecture. Not very long, but we have to get into a little bit a more complicated topic next, which is the conservation of angular momentum. So stay tuned for that. And also, there will be a problem set associated with angular momentum, so make sure you do that assignment.